Good morning, class. Let's get going. I have few reminders, as always. There's a project milestone starting, not starting, due on October 20th. That's about 5 days from now. So for that, you should have had one submission on Kaggle, as I mentioned before, and a short report. And as of this morning, the highest score on the Kaggle leaderboard is about 80%. It's inched up slightly compared to last week. So it's interesting to see how that goes. Also, there's homework 4 on Canvas. This is going to be entirely on learning theory, and it'll be due in 2 weeks. So basically, it'll cover everything that we have done in the last week and this week. And this does not involve any programming, but I've been told this might be, depending on how much you like math, either a very easy homework or a very hard homework. So you know where you stand. So based on that, you want to give yourself time. Um, so are there any questions? I see there's already one. So in part 1, in homework 4, are the features binary? Yes, the features are binary. It says so in the first paragraph, the second paragraph of the question. So you have n Boolean features, and we want to build decision trees with a depth limit. So the general point of this homework is that question is to think about how um, where you, well, it does say about Boolean features in the first paragraph. Um, so the general point of this question is to think about where and how we can apply the various pack learnability results that we have seen. So for example, in um, we looked at already two pack learnability results, one that involves consistent learners, the other one that involves agnostic. And in both cases, as I will mention again today, the key quantity that we need to measure is the size of the hypothesis space. So if you can count the number of functions there are, then you can essentially plug it into one of those two bounds and decide whether that will help you decide whether something is pack learnable or not. And this is what we saw in the last lecture also, when we looked at the positive and negative learnability results. When the log of the size of the hypothesis space is more than polynomial, we declare it as not pack learnable. Otherwise, it's not. Otherwise, it is learnable. So in this question, essentially, the questions are stepping you through this process of counting the number of decision trees. Um, and in fact, if you're careful about the question, you will note that actually it's overcounting the number because there are two decision trees, maybe different from each other, may look different from each other, but give you the same function. As far as this question is concerned, we don't care. If they look different, they count as different trees. And that's like an overestimate. And the question is to see whether even that overestimate is polynomial. If that's polynomial, then life is good. So that's the general theme. So are there any questions? So I see that there's this comment and thing about, are the features binary? Yes. If you look at the bottom of page 1, it says there are n Boolean features. Are there any other questions about the homework or project or anything else? So the second and third part of this homework is talking about stuff we'll cover today, about shattering and VC dimension. And there's an extra credit question about decision lists. Now this is it's introducing this new class of functions called decision lists and asking you about whether they are pack learnable or not, and whether they are linearly separable or not. That question could be tricky. It's fun, could be tricky, and um, that's why it's extra credit. And I'm not going to. I don't expect all of you to have seen the homework yet. So if there are any questions about that question or anything else, come to office hours. We can chat about it. And we can this homework might be it's more like an algorithms or a math style homework than just programming. So allocate as much time as you need for that. Any other questions, comments, suggestions? If not, we're going to pick up where we left off. In the last class, so we are still talking about computational learning theory. And as I mentioned, we're going to talk about this notion of shattering and VC dimensions, just to kind of step back up and see where we are. We're talking about computational learning theory, which is the theory of generalization. Throughout this unit for the last week and this week, the question that we've been asking ourselves is, given the training set, if you have this much of this big of a training set, what can we say about the classifier's ability to generalize? To formally state that, we saw this definition of pack learning, and we saw a theorem that we called Occam's razor, which essentially said if you have these many number of examples, then with high probability, you'll be able to, um, uh, with high probability, you'll find a classifier that has low error. And we considered two separate situations. We considered the case where the learning algorithm is guaranteed to find a classifier that's consistent with the training data. This is like your decision trees if you let the tree grow as much as possible. And then we saw another case where we considered the situation where the learning algorithm is exploring a hypothesis space that need not contain the concept. So what that means is that we are searching for a classifier. We don't know what the true classifier is, so we are constructing an approximation, and we don't even have any reason to believe that our approximation is going to be perfect. It's going to have error even on the training data. So we're going to ask, how much worse could it do in the future? In both cases, we're asking how much worse could it do in the future. And we looked at a bunch of positive and negative learnability results, primarily around the consistent classifier case because it's a little bit easier. But the underlying approach is essentially the same. So the main point that we noticed is learnability depends on the size of the hypothesis space. So really, we are considering how big is the hypothesis class. So there's a question: does negative learnability mean sample or computation speed grows faster than polynomial? That's right. So if either the sample complexity or the computational complexity for learning is bigger than polynomial in 1 over epsilon, 1 over delta, and the dimensionality and the size of the hypothesis space, we call it unlearnable. What does that mean? When sample complexity grows faster than polynomial, that means the number of examples needed to find a good classifier with high probability is extremely large. So it's not going to really scale. You can't scale learning from that point of view. You're going to need more examples than you can manage. From the computational point of view, the negative result says maybe there is this set of examples may contain enough information to find a classifier, but the process of searching is going to be so complicated. We are not searching over examples, we are searching over functions. The process of searching over functions is so is so complex from the time point of view that learning is not going to work. And these, some concept classes are learnable in the sample complexity sense, but not in the time complexity sense. Some concept classes are not learnable even in the sample complexity sense. So, that just means that we need to do something else. Okay, so today we're going to talk about shattering and VC dimension, and the setup for this is something that we saw at the end of the last lecture. So we saw, actually, both of these are Occam's razor results. This is Occam's razor for agnostic learning. So we saw essentially Occam's razor theorem that says when the hypothesis space contains the true concept, If you have these many examples, m greater than this number of examples, then you have a good, there is a good classifier. In the agnostic setting, when the hypothesis space may not even, when we don't know whether the hypothesis space contains the true concept, if you have more than these many examples, then you have a high chance of getting a good classifier. In both cases, the key point to note is in terms of the size of the hypothesis space, the complexity depends on log of the size of the hypothesis space. So in some sense, if you have a new set of functions, and this is what your homework is asking you, this is a set of k decision trees, depth k decision trees, find the size of the hypothesis space, take the log, and plug it into this thing, one of these things. The homework also asks you to decide which one you should plug it into. Now, the question that's kind of not clear is um, what about linear classifiers, for example? We've seen linear classifiers. We can't count the number of functions. So clearly we need something else. So there's a comment, should the greater than in Occam's razor be greater than equal to? Sure, yeah. So, okay. So the problem is we don't have any way of handling things like linear classifiers in this theory. So we need to essentially grow our theory, and that's what we're going to do. We're going to now look at this new idea called shattering and talk about how this gives us the definition of something called VC dimension. And finally, I'll present analogs of these two kinds of results, but that they use the VC dimension of a hypothesis class. Let's get started. And this is kind of I personally like this lecture, this topic, simply because it's fun. All the problems in this that we will encounter here are like little puzzles that we can solve. So, as I said, the previous analysis was restricted to finite hypothesis spaces. So, what about infinite hypothesis spaces? How can we handle that? And there are many infinite hypothesis spaces. In fact, most of the time, when we actually use machine learning, we'll be using infinite hypothesis spaces, like linear classifiers, for example. A linear threshold function, there are infinite number of hyperplanes. Or we can have a combination of linear threshold functions, which if you look at neural networks in a certain light, when we'll get there, you can think of it as a combination of linear threshold units. Or maybe we want to draw rectangles around the positive points and say all the positive points are contained inside a rectangle, or maybe convex polygons. All of these are objects that are infinite in number. So if they are infinite in number, the notion of using the size of the space of functions is a meaningless thing because they're all infinite. So we can't just plug in infinity to that thing. If you have an infinite number of examples, then you'll have a good classifier. That's what the rule, that's what the theorem says. That's a meaningless statement. So in some sense, the analog of the log of the size of the hypothesis space, in this case, is something called the Vapnik-Cherenkis dimension, or the VC dimension. It answers the question, what's the expressive capacity of a set of functions, any set of functions? It doesn't matter if it's finite or infinite. In fact, one of your homework questions asks you to connect the VC dimension or find the VC dimension of a finite hypothesis class. You're given a set of functions. How expressive is it? So you'll sometimes in the literature around this thing, you might see the phrase or the word capacity. What's the capacity of a concept class? It's analogous to the size of H. Actually, it's analogous to the log of the size of H. So let's get started with an example here first before we jump into any detail. So let's say that the target concept is an axis parallel rectangle. What that means is all points inside, so the true concept is a rectangle, and all points inside the rectangle are labeled positive and all points outside are labeled negative. The goal of learning is to find the rectangle. Okay, that's the game. Maybe you're given a data set that looks like this. So you have positive points and negative points. And I just so that we remember what the true concept is, I've got the true rectangle on the slide. So we have positive and negative points. And based on this, maybe a reasonable classifier is to say, yeah, a rectangle that goes around all the positive points is the classifier. So, this labels the entire training set perfectly. But maybe if you have a different data set with these 4 points instead of 2, you might find a larger rectangle. It's not always the case that if you have more points, the rectangle gets larger. Sometimes you might have a data set with more points and the rectangle stays the same. You could, essentially you can think of, you can even imagine that there's a learning algorithm here where you kind of you find the farthest uh, bounds of all the positive points and draw a rectangle around that. That's your learning algorithm. So for example, we might have found this rectangle here. The question that I want you to think about is, if the target rectangle is this entire thing, will we be able to learn the rectangle, the true thing? Will we be able to identify it exactly? Or can we only ever hope to come close? So I've launched a poll. Why don't you just take a guess? Okay, that's true. Okay, I'll switch it up the next time. So there's a comment that says in the poll, just looking at the question length gives you the right answer. I'll make sure I will switch that up in the next poll. Okay, I think about 3/4 of you have voted. So in the interest of time, I'm going to end the poll. Most of you say that the true rectangle, it's unlikely we'll ever learn the true rectangle, but we could come close. And that's correct. So here's, I mean, for just to kind of make sure that it's not confusing, imagine that we are not in this weird scenario where we get a training point that's exactly on the rectangle. Let's ignore that situation because that is a rather remarkable thing. Instead, let's say we find a point that's really, really close. So let me zoom in here. Let's say we find a positive example that's really, really close. No matter how close it gets, we can always find some, there will always be a gap between the true rectangle and the rectangle that we draw, no matter how close it gets. So it could, this is because the real numbers are dense. So you could keep going, taking this closer and closer. It may seem like it's the same rectangle, but there will always be a gap unless the point is exactly on top of the rectangle. So we can come close to it, but we won't really, other than the situation where we get a training point on the boundary, it's almost extremely unlikely. That's a unnecessary amplification. Almost extremely. It's extremely unlikely. So it's extremely unlikely that we'll ever learn the true rectangle. But we can come arbitrarily close. For any epsilon, maybe we find a training point within that thing. So we can come close to the true rectangle, but never learn the true rectangle. Okay, given this situation, can we think about expressiveness? Because here's the thing, the rectangle that's covering all the positive points is correct. It's clearly a correct classifier, but so is this rectangle that I'm drawing right now. Well, almost a rectangle. What we have to think about is, do we really care about the exact rectangle, or do we just care about can we just think about different kinds of rectangles as being equivalent as far as this training set is concerned? And we can do the latter because these two rectangles are equivalent, the outside one and the inner one that covers the data are equivalent, because both of them separate the positive and the negative points, but they are not identical. So we need to go beyond identical classes. This we need to go beyond this idea that we will find the exact classifier that nature has in its mind and think about equivalence classes. We'll find another classifier that is equivalent to this. So let's think about, let's look at any questions. There's a comment. I can only see the problem arising between testing example that is in the margin. So yes, the only place where these kinds of things would make mistake are in these margins here, in this gap. Yes, you're right. So as you get closer and closer, the margin gets thinner and thinner, and as a result, there will be it's less likely that you'll make a mistake. But even before we talk about training and testing, let's talk about whether rectangles are more expressive than, say, lines. So let's think about the expressiveness of functions. Suppose we have these 2 points. A question that we can ask is, can a line correctly classify any labeling of these 2 points? Can a linear classifier separate any labeling? What do I mean by any labeling? There are 4 possible ways to label these 2 points. You can have, I'm using circles and triangles. You can have, both points have the same label. It could be a circle or a triangle, or both points have different labels. These are the only ways in which you can classify these 2 points. And now the question is, can we draw a line that puts all the circles on one side and all the triangles on the other side, in each case separately? And the answer is, of course, yes. In every case, if the 2 points are labeled differently, I can put the line in between them. So that's this case and this case. If the 2 points are labeled identically, I can put the line on one side, just away from them. So there are many such lines. This line, say, if you're pointing towards, let me just imagine that the line always points towards the circles. So this case is here and this way. So there are 4 ways to label these 2 points. And in every single case, we can draw a line that separates the positive and the negative points. In order to give this property a name, we're going to say that linear functions are expressive enough to shatter 2 points. What does shatter mean? In every possible way in which we label these 2 points, it's possible to draw a line. If this happens, then we say the linear functions can shatter 2 points. There are 2 points, and irrespective of how they are labeled, I'll find a line that agrees with that labeling. Maybe this is, why does this concept need a name? Let's look at 14 points instead. So these 14 points in particular, let's say. So you have these 14 points, and let's say I label them this way. If you label them as shown on the slide, then you can, of course, this is linearly separable. I can draw a line that separates them. This does not mean that it does not satisfy the definition, because there is this labeling here, which is much, much more complicated. No matter how you try to place a line, this is not going to, you can't separate out the triangles from the circles. So the lines are basically 14 points, cannot be shattered. Linear functions are not expressive enough to shatter 14 points. There is at least this one labeling and many more, not the point, but this entire labeling here of points where there is no line that can separate out triangles from circles. So linear functions in 2 dimensions are not expressive enough to shatter 14 points. All you need is one example of that kind. Does this mean that these 14 points can never be separated from each other? Of course not. There are more complicated functions that can actually separate them. You can always find gaps between these things and keep drawing circles all around. And what this means is, intuitively, a linear classifier is less expressive than the set of classifiers that look like this curve. So if I imagine this family of classifiers that includes this curve, all curves of this kind, then this family is more expressive than just linear classifiers. So lines can't. This is another way of saying the same thing. 2 points can be shattered by both lines and curves. 14 points cannot be shattered by lines. So let's formally define this, and we look at a bunch of examples. Given a set of examples, a set of points, we say that this particular set is shattered by a set of functions. So we are given two sets. We have a set of examples and a set of functions. We say that the set of examples is shattered by the set of functions if every single way in which you label the functions, the examples as positive and negative, no matter how you label the examples as positive and negative, there is a certain function in this set that gives exactly the same labeling. So no matter how you label examples, you will find a function inside the set that will also agree with your labeling. That's what we did with the linear classifiers in 2 dimensions, right? No matter how these 2 points were labeled, I could find a line. My set of functions is a set of lines. I could find a line that perfectly agrees with uh, the labeling. This then we say that that particular set, not necessarily all sets of 2 points, that particular set of 2 points can be shattered by the set of functions we are considering, in that case, lines. And the intuition here is if you can shatter a large number of points, or if you can, if a function, a set of functions h that can shatter a large number of points is more expressive. So this definition here, notice that in order for us to say that a function shatters a set, we need to consider every single partition of the examples. Okay, let me walk through an example and then pause for questions. So suppose you have a simple hypothesis. Let's consider something really, really simple here. Suppose you have a hypothesis class. I'm calling it left bounded intervals on the real axis that assign the instances for this problem are points that are greater than 0 anywhere on the line. What this class of functions does is every function is defined by a single number a, which is a positive number, and points between 0 and a are labeled as positive, and the points outside are labeled as negative. It's a class of functions. So this classifier here would say this is positive, and everything outside is negative. And if you change a, you'll get a different classifier. So we can ask, we can now start thinking about, let's take a few sets and see if it shatters things. So let's say we have a set with only 1 point, that point there. It doesn't matter where it is because 1 point anywhere on the positive thing, on the positive real line. So let's say you have a set with that 1 point. We can ask, does this set get shattered by this by the class of left bounded intervals? In order to do that, we need to consider every possible labeling of that point. So first let's consider the case where the point is labeled as positive. If the point is labeled as positive, I can find an A that's just outside that contains this. So A greater than whatever that point is. If you find that A, then this whole region is positive. In particular, that point is also positive. So this particular classifier defined by A correctly labels the point as positive. Instead, if the point was labeled negative, you can still find A that labels the point as negative, because all you do is you put A to be less than that point. So this, irrespective of whether the point is labeled as positive or negative, we can find a classifier that perfectly separates the well, not separates, that perfectly assigns the label. So if a slightly more formal way of saying this is a set of 1 point, or any set with 1 point, can be shattered with the hypothesis class of left bounded intervals. So now let me pause for questions, because this it's going to get a little bit more complicated soon. So let me pause for questions. And usually this is a lecture which ends up being pretty interactive. Unfortunately, the medium that we are using is less interactive than I would like, but do ask questions. Is there a hypothesis class that cannot shatter one point? Well, the empty set, for example, cannot shatter one point. There are, yeah, I mean, that's a trivial example of a set of functions that cannot shatter one point. Can I give more examples about any partition? Yes, in fact, that's going to be the next use case. With one point, this notion of any partition becomes a little bit, it's not very obvious. Let's consider 2 points. Suppose you have a set with these 2 points. We can ask again, is this class of functions, can this be shattered? Now, for that, we need to consider every possible partition of these 2 points. So let's say, what do I mean by every possible partition? It's essentially saying, let's name these points A and B. I can partition the points into positive and negative by saying A is positive and B is positive. That's one partition that says both are positive and nothing is negative. This is plus and this is minus. This is minus and this is plus, plus and plus. These are the 4 possible ways in which we can partition the points into positive and negative. So this means that, so let's look at, there are many comments. So instead of thinking about any partitioning, you can think about any labeling of the points. Think of it as for any labeling of the points. When we are defining when we are defining shattering, we don't get to pick the partition, the labeling. So for every possible labeling, we need to find a classifier. Now let's actually work through this case. Let me see if there are any questions that I need to answer right away. So A cannot be negative, and I'll get to the other questions later. I'll get to the other 2 questions later, because I think that's taking us to where we want to go anyway. So let's consider the 4 possible cases. So first, let's consider when we have, I'm going to draw all of them here. So let's say we have, this is A and B, so you have plus plus. If I have plus plus, then I can choose the classifier which is defined with a little a to be somewhere here, and that says everything inside this is positive. So yeah, if both points are labeled as positive, of course you can do that. What if both of them are labeled as negative? So if both of them are labeled negative, so you have minus and a minus, then I can put the A on the inside and this works. Let's consider the third case when the first point is labeled as positive and the second one is labeled as negative. Then I can put the A in between and say everything inside that is positive. Now, the fourth case, and this is the case that I think Ashton was talking about, is the problem one. So if I make this negative and this a positive, then we are in trouble. We can try to label the points, but it's not going to work. So if the inside point is negative and the outside point is positive, if I put the A here, then it incorrectly labels the example because it says everything here is plus and everything here is minus. So it incorrectly labels the second point. Okay, so let me try to force the label of the second point to be correct. So I'm going to put the A all the way outside, but that means everything here is positive, and this point is labeled incorrectly, the first point. There's only one other place where you can put the boundary, that's in between them, but unfortunately that just makes things worse. So if you put the boundary in between them, you say this is positive, and you can make a mistake here. You say this is negative, and you make a mistake here. So everything is incorrect. What this means is for the labeling where you have a minus plus, there is no classifier in the set of functions that agrees with that labeling. So let me look at the questions, and feel free to ask more questions. So shattering sounds like a verb, but in practice it looks more like a property of the relationship. It is actually a property. It's also convenient to you call it a verb because I can say this set of functions is shattered. Sorry, this set of points is shattered by the set of functions. But you can also think of it as a property, but that says given a set of points and a set of functions, does this property hold? What property? For every possible way to label those points, the set of functions contains a representative that can agree with it. So it is technically it's more appropriate to think of it as a property, but it's used as a verb in this, but not as an operation. It's used as a verb in the sense that this functions shatter the set. So there's if you always guess the opposite label, can that not be considered correct? Practically speaking, yes, but for here, no, for the following reason. In this case, we are not allowed to guess the opposite label because if we had to guess the opposite label, then we are changing the class of functions. We are introducing, we have essentially changed, we don't care about whether we get the labeling right or not. We care about this particular set of functions, and we are trying to understand its properties. So just so that others follow the question, I think the question was, in this particular case, if the point, let me draw the, so if this point, the ground truth, I'm going to write the ground truth at the bottom. The ground truth for this, not the ground truth, the labeling that we are considering, oh, it's actually here. So this point is negative and this point is positive. But the prediction is this is plus and this is minus, which means all you have to do is flip the sign and you get the true label. It seems like this particular classifier knows the true label, it just gets the sign wrong. So you can flip the sign. But the act of flipping the sign essentially changes the classifier because it's a different classifier. That classifier that would flip the sign is not inside the set. That classifier actually would look something like this. Everything here is positive and everything here is negative. That's not in the set we are considering, so we cannot do that. So that's an interesting point. So let's see, if a classifier always gets it wrong, can we just negate its output? That's the same question. So there's another comment that says, I think this would still break once we add one more point to the set. Yes, we don't need to add one more point to the set because as we will see, we just stop when it breaks. We don't consider larger sets. So what this means is, we have essentially what we have proved is two separate statements. All sets with one point can be shattered. Any set with one point can be shattered. That is, given one point, for any labeling of the point, we can find a concept in this class that is consistent with it. We can find a classifier that can give it a positive label or a negative label. There are some sets with 2 points, or any set with 2 points cannot be shattered. So any set with 1 point can be shattered. Any set with 2 points cannot be shattered. Why? Because given 2 points, you can always label them in such a way that no function in the concept class will correctly classify it. So all you need is just one labeling. One bad labeling is enough to declare that the set cannot be shattered. And here, to show that it can be shattered, we need to consider every possible labeling. So let's let's move on, because there's this set of functions, as entertaining as it might be, is not a particularly useful set. So let's move to a slightly bigger set. I mean, not particularly big, but just ever so slightly more. This time, we're going to consider um, an interval. The hypothesis class is an interval defined by two numbers, a and b, and the way the hypothesis class function is, if an instance lies in between the a and b, if a less than x less than b, then you label it as positive. Otherwise, you label it as negative. So everything in the shaded region is positive. Everything outside the shaded region is negative. And the way we get to pick a function is we get to choose a and b. We choose the bounds, either it shrinks or it grows or so on. So we can play the same game again. We can ask, let's go through the process from the beginning. First, can it shatter one point? So we are given a line. I have just one point here. We can ask whether it shatters it. So for that, we need to consider every possible labeling. Thankfully, there are only two possible ways to separate, partition this point into plus or minus. Either this point is a plus or this point is a minus. And now I can ask, where should the boundaries be? Well, if the point is a plus, we know that it should be the A should be on this side and B should be on this side, because everything in between is positive. So there is a classifier that can agree with that labeling. If it's a minus, we can just put the boundary outside. This is A and this is B. And at this point, everything inside is positive and outside is negative. So what this means is, no matter how this one point can be labeled, we can shatter it. So all sets of one point can be shattered. By the way, even though here I'm considering this one point could be anywhere on the real line. So all sets of one points can be shattered. Okay, now let's consider the next case where we have 2 points. Remember, 2 points is the case that broke the previous example. So let's go through this a little more carefully. So you have, let's say we have 2 points. Can 2 points be shattered? So again, to prove that 2 points can, or to check whether 2 points can or cannot be shattered, we need to consider every possible labeling. So we have plus, 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 minus, minus, plus, and a minus, minus. And the question that we are exploring is, can I find this bracketing A and B that gets all the pluses inside and all the minuses outside, in each case separately? So in the first case, I can put a bracket around both the pluses. So that works. In the second case, I can put a bracket around this one. The third case, I can put a bracket around this one. And the fourth one, I can just put it outside anywhere I want. In every single case, only the pluses are contained in the bracket. By the way, when I say bracket, I just mean this is an A and this is a B. The line looks like this. So only the pluses and the minuses are inside the interval. Sorry, only the pluses are inside the interval and all the minuses are outside, irrespective of whether the first point is a plus or a second point is a plus or neither. So what we have shown is 2 points can also be shattered by this particular set, which is interesting. The only difference between this set of functions and the previous set of functions is, in this set, the left end of the interval is not fixed. We get this freedom of moving A around. In the previous case, the A was fixed to 0. And suddenly, this particular set we find is more expressive. The first set, the set of functions, the first hypothesis class we considered, half left bounded intervals, was not expressive enough to shatter 2 points, whereas all intervals, a set of real intervals, is expressive enough to shatter 2 points. Okay, this seems exciting. Let's see if we can do more. Let's consider 3 points now. Can someone predict what will happen here and use the chat? We have to now consider every possible labeling. So I'm going to be writing all possible labelings. So you have plus, 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 minus, minus. What have I done here? I should be more systematic. Okay, I think many of you have saved me the trouble of writing everything. So I will just follow the advice. If I put a minus here, we can, in order now to consider that, in order to show that this is not going to work, we need to now consider every possible function. Like, we need to consider every single function inside this set and show that not one of them will work. Well, thankfully, we don't have to consider every single function. We can just go around by trying to put the bracket around. If I put the bracket around this plus, it's going to fail because this one's wrong. If I put the bracket, if this is my interval, it fails. If this is my interval, okay. In the first case, you make a mistake here. The second case, you make a mistake here. And in the third case, where we put all of these together, we make a mistake here. These are the only way in which we can attempt to cover at least one of the positives. Any other interval we consider will cover neither of the positives. So essentially, what this means is the set of real, if we consider 3 points, there exists one labeling, namely this particular labeling that doesn't get shattered. This labeling that doesn't get correctly classified. Even if one labeling doesn't get correctly classified, we say the set is not shattered. The set of points is not shattered by the hypothesis class. So again, there's a comment about if we had negation, life would be good. But if we had negation, it's a different class of functions. So just so that you don't have to live with my writing, I've drawn it in the slide. If in particular for the set of intervals on the real axis, this labeling is adversarial, the plus minus plus. So the proof essentially enumerates all possible 3 points and every possible labeling. We don't need to enumerate all possible 3 points because any 3 points on the line is a representative because they all essentially look the same. And then we need to enumerate every possible labeling to find this one adversarial case. Now imagine that this seems like an easy situation, right? We are basically going through this game where we are trying a set of points and now considering every possible labeling. Maybe this is just too easy. To convince you that it's not, let me go to our dear friend, linear classifiers. It's still easy, but it involves a little bit more thinking. So let's consider half spaces on a plane, or basically linear classifiers in 2 dimensions. So in order to consider whether a linear classifier can shatter a certain set of points, we need to consider that set and try to assign every possible labeling to the points in the set and see where it goes. So so let's go one at a time. Can one point be shattered? Maybe you can just type your answer in the chat. So there's a question, is this not similar to the definition of being linearly separable? It is kind of similar. No, actually, I take it back. It's not about being linearly separable or not. Yeah, we are asking whether no matter how you label the points, that particular labeling is linearly separable for this particular set of functions. So most of you, well, 5 of you have said yes for can 2 points be shattered. I just realized also that Zoom allows you to raise your hand. I've never used that, but let's not. If you want, you can also, instead of saying yes, you can also raise your hand. Um, but so what we have is 1 point can be shattered, and to prove that, it's rather simple. So you can have plus. If that 1 point is a plus, you put your line and that's there. If that 1 point is a minus, you just make the line face the other way. So that's easy. We saw earlier that 2 points can be shattered. Why? Because no matter how you label those 2 points, it'll work. Let's consider 3 points. Can any set of 3 points be shattered? In fact, that's one of the questions your homework is asking you. Let's there is already a disagreement in the chat about um, yes and no. One person says yes if n less than 3, otherwise no. Adam says n less than equal to 3. So maybe there's some misunderstanding. 3 points in a straight line. So there's a suggestion. Let's consider 3 points in a straight line. Let's consider these 3 points. Okay, let me draw a line and then draw the points. That will at least, so I have a line. Let's consider these 3 points. Now, what happens? So why did you suggest that? Can you suggest a labeling for these points? That's not going to work. Remember, by the way, I have 2 dimensions to play with, so my line can go anywhere. So there's one suggestion that's a minus, plus, and a minus. Another one is a plus. Let's go at it. Let's go at them one at a time. So if I have a minus, plus, minus, I need the plus to be on the correct side. So if my line does not intersect with it, so it can go this way, then it misclassifies this point and this point. So that's not good. Similarly, on the top, if I get my line to go this way, it misclassifies this point. And if I get my line to go this way, it misclassifies this point. So these 3 points, this particular labeling cannot be matched by any line. And I think it's the same for the other case also. If you have a plus, minus, and a plus, you can essentially enumerate different ways in which the line can fit, and you'll get a simple counter example for every possible line, for every possible line that you try to put this. So these 3 points cannot be shattered. Does this mean no 3 points can be shattered? So can you think of an example where some 3 points can be shattered? We just need one example. What would be okay, Adam says consider 3 points that are not collinear. So let's consider 3 points that are not collinear. So you have any 3 points in general, or collinearity is a rather special thing. So let's consider these 3 points. Now, what happens now? So can every possible labeling, in fact, let me make the claim and leave it as an exercise because it's also in your homework. I claim no matter how you label these points, you'll be able to find a line that separates out the positives and the negatives. And in fact, one of the questions in your homework asks you to consider every possible labeling. So there are 3 points, so there are 8 possible labelings, something like this, for example. There are 8 possible labelings, and each case, I want you to show me a line that separates those, separates the positives and the negatives. And the answer is yes. If 3 points are not collinear, it can be separated. 3 points that are collinear cannot be separated. But remember, shattering is a property of a set of points and a function. So we say, more generally, collinear. I don't know if collinear has a single L or a double. So I'm just going to write 3 points on a line. So 3 points on a line cannot be shattered by half spaces. Half spaces is just a line, right? I mean, a line divides the space into two halves. 3 points otherwise so there's apparently it's two else. Okay, so that's useful. So let me then make use of my newfound knowledge. Non-collinear points can be shattered. So there is some set of 3 points that can be shattered, namely non-collinear points, and there are some set of 3 points that cannot be shattered. Well, this is just a fact of life. There's a comment. There seems to be a relationship between the number of points that can be shattered and the degree of the classification function, or the degree of the polynomial. Instead of a line, if you use a quadratic function, it can be shattered. And you're absolutely right. What that really means is that quadratic functions are more expressive. This is really what we're trying to get to. This is the intuition that we are building up towards. Some function classes are more expressive. Can we put a number to it? And we'll get to a formal definition of that, but essentially that intuition is what takes us to VC dimensions. But before we go to VC dimensions, let's consider 4 points. We've already shown that in 3 points, some of them can be shattered and some of them cannot. What about 4 points? Let's consider, let's work through these 3 cases, okay? So for 4 points, we can consider 2 situations. Case 1, 3 of them are a line. If 3 of them are on a line, the other one is not. So you have 3 points on a line, and the other one is not on this line. It could be anywhere else, somewhere like this. In this case, I can find a certain labeling that is not going to work. In particular, the labelings that were suggested, something like plus, minus, plus. I don't care what the labeling of the 4th one is. Let's make it a plus. Doesn't matter, because this itself is going to make life hard for a linear classifier. So this, if any 3 of the 4 points are on a line, they cannot be shattered. Let's consider the other case. No 3 are on a line. If no 3 of them are on a line, that means 3 of them form a triangle, and the 4th one can either be inside it, or 3 of them form a triangle and the 4th one is outside it. These are the only 2 ways in which 3 points cannot be on a line. Either, if no 3 of them are on a line, let's pick any 3 and make a triangle out of it, and then you get these 2 situations, right? So now let's call this A and B. For A, can someone suggest a labeling of the points that's going to pose problems for a linear classifier? A minus in the middle and the plus everywhere else. You're right. Another, it's a similar other problem case would be a plus in the middle and a minus everywhere else. Basically, if the middle point has a different label from the outside points, no matter how you draw the line, you're not going to get the correct label. So that in that case, so that means, so let's write this down. This is cannot be shattered. This also cannot be shattered. So when I'm saying, remember, this is where it gets confusing. To show that this set cannot be shattered, all you need is one counterexample, one labeling that is going to fail. So You need one labeling that fails, but for 4 points, we need we have not yet exhausted everything. Maybe these 4 points. So 4 points, you don't have a case where three of them, the fourth point is inside the triangle, but outside. So something like this, and this is similar to what is on the chat also. So you have case B where all four of them, the fourth point is outside the triangle. Now what happens? Can someone come up with a labeling that's going to be a problem? This is like your XOR case. So you can just you can put a plus minus or something like that. There are basically you go around in a circle and keep giving alternate labels, and this is the famous XOR case. This cannot be shattered. And here is where something gets people get a little bit confused. If I'm saying that this cannot be shattered, of course there's a labeling, there's a different labeling that can be correctly classified, right? So if I make this a plus, and I can draw a line here that separates out the pluses and the minuses. But we are at this point looking for a counterexample. We are looking for a labeling that is going to defeat our hypothesis space. If we can find one, then this cannot be shattered. So now look at what I have proved here. I claim that no 4 points can be shattered. Why? Because 4 points can either, if you have 4 points, some 3 of them are going to be on a line, or no 3 of them are going to be on a line. This is exhaustive. Only one of these two situations can happen. If some 3 of them are on a line, cannot be shattered. If no 3 of them are on a line, then either the fourth point lies inside the triangle or outside. These are the only two cases. In the first case, it cannot be shattered. In the second case, also it cannot be shattered, which means no arrangement of 4 points. It doesn't matter how you place the 4 points on a 2D plane, it cannot be shattered. So what we have shown is 4 points cannot be shattered using a single, a linear classifier. 3 points is kind of a mixed thing. Some are, there exists some arrangement of 3 points that can be shattered. There exists some arrangements that cannot. In 4 points, in the case of 4 points, there's no such confusion. No arrangement of 4 points can be shattered. So is there a way to measure, there's a comment, is there a way to measure the entropy of the labeling? It seems like when the labelings are mixed in with other labels, you need a more complex function. Maybe there is, but I think you're also thinking of this particular class of functions. Maybe there's a certain other class of functions that is good with things like XOR and not good with things like conjunctions. So you have to be careful with that line of thinking. In any case, so when we come to half spaces on the plane, what we have is 4 points cannot be shattered. That's the result. So you can think of shattering as this sort of an adversarial game between you and an adversary, where you claim that you have a hypothesis space that can shatter a specific set of D points, a given set of D points. And the adversary says, adversary gives a label that defeats you. And when I say adversary, I mean essentially it's the worst case. It tries to find a labeling that defeats you. But then if you can find a classifier that agrees with the labeling, then the adversary loses. But if you cannot find a classifier that agrees with the labeling, that means that your original statement was wrong. That means that the hypothesis class cannot shatter this set of functions. Now, the reason we're talking about shattering is because, as many of you noted in the chat, it's telling us something about the complexity of functions, the capacity of functions to support a certain complexity of labeling. Intervals could only shatter 1 point, half intervals. Full intervals could shatter 2 points, but not 3. Linear classifiers in two dimensions, that's important, could shatter some set of 3 points, but no set of 4 points. And of course, once you do 4, you don't need to keep going up. You don't need to go to 5, because once 4 fails, 5 is just adding one more point. Who cares? It can be any label it wants. So what is amazing is that there are some functions that can shatter an infinitely large set. What does it mean to shatter infinite points? For any finite subset, if it can be shattered by a hypothesis space, then it shatters an infinite number of points. You can think of the number of points a function shatters as, in some sense, the bias it encodes. When I say bias, I don't mean the bias as in the linear classifier, but this is in terms of inductive bias. It's preference for, you can think of it as the simplicity of a classifier. An unbiased hypothesis space can shatter the entire instance space. It can, no matter how the instance space is labeled, this unbiased hypothesis space will find a labeling that matches it. So for example, if I grow a decision tree to arbitrary depth, no matter how your training set is labeled, you will find a decision tree that agrees with it. However, if the which means that, if a larger set of points can be shattered, we say that the hypothesis space is more expressive. However, if you have a weaker classifier, meaning a classifier that cannot shatter a large number of points, then it's going to be, it gets interesting, right? If a classifier cannot shatter a large number of points and yet it achieves a low training error, that means that there's something, it seems like you've discovered a regularity in the data. A classifier that's not expressive enough to shatter a large number of points, and yet imagine you get zero training error for a large number of points. That means that that particular labeling is something special. That means that you found a classifier, you found an underlying truth. This is, again, we are going back to this Occam's razor style philosophy. This idea is going to give us the definition of the VC dimension. Just to remind you, I've kind of rewritten the formal definition of shattering here. A set of examples is shattered by a set of functions if for every partition of the examples into positive and negative, there's some function that gives exactly the same label. The VC dimension of a hypothesis space is the size of the largest finite subset of the instance space that is shattered. In other words, if there is a set of examples of size D that can be shattered, then we say that the VC dimension is at least D. Even one subset will do. Even if you can find one arrangement of the points that can be shattered, then the VC dimension is D. If not even one arrangement of the points of D points can be shattered, then VC dimension is strictly less than D. So every VC dimension proof typically comes with both sides. There's a lower bound. You need to show that there exists one set of points that can be perfectly classified. And there's an upper bound that says no arrangement of these points can be classified. So you need, by sandwiching these two things, you can show that the VC dimension is some number D. We've already, actually what we have done is we've already proved 3 different VC dimension results. For the set of half intervals, the VC dimension is 1. There is a data set of size 1 that can be shattered. No data set of size 2 can be shattered, so the VC dimension is 1. For intervals, which are these things, there's a data set of size 2 that can be shattered, and no data set of size 3 can be shattered. For half spaces on the 2D plane, the VC dimension is 3. There is some data set of size 3, one arrangement, in particular the triangle, that can be shattered. And by considering the various cases in which 4 points can exist on a plane, I showed that no data set of size 4 can be shattered. So VC dimension of half spaces is 3. Now, in general, and I'll just say the result without proof. In general, for a linear threshold unit in D dimensions, the VC dimension is D plus 1. In 2 dimensions, it is 2 plus 1, which is 3. For neural networks, VC dimension can tend, we've not seen neural networks yet, but Neither of these we have encountered yet, but I'll just tell you the result so that when we eventually encounter it, you can come back to this. For neural networks, the VC dimension is roughly, I mean, there are different things to consider, but it's roughly the number of parameters. This is a very weak statement. It depends on a lot more things. For nearest neighbors, which might be the last classifier we'll see in the class, VC dimension is infinite. Uh, Interestingly, the number of parameters needed for linear classifiers is also d plus 1. The VC dimension it behaves like the number of parameters, even for linear classifiers. For neural networks, it turns out that there is more. VC dimension is not sufficient. There's optimization issues we have to worry about. And when we come to nearest neighbors at the end of the semester, I want you to think about this. Why would this be infinite? So, are there any questions? We haven't proved any of the results on this slide, but we did prove all of the results on this slide. And in your homework, you'll be proving more things about VC dimensions. So didn't we show that this is the place where with VC dimensions things get more complicated, confusing. There's a question. Didn't we show that with 3 points you couldn't shatter it if it was collinear? That is true, but the definition of the VC dimension is it's saying all you need is one set of D points that can be shattered to say that the VC dimension is D. All you need is one. We had this one set, right? Points that were not collinear. If we can find one set of 3 points that are not shattered, that are shattered, then the VC dimension is at least that much. So the fact that 3 collinear points cannot be shattered is less interesting because of the fact that 3 points that are not collinear can be shattered. As a result, VC dimension is at least 3. So this is so I want you to revisit this lecture afterwards and think about how the quantifiers line up. With 4 points, I showed that no matter how 4 points exist on a plane, it cannot be shattered. Every arrangement of 4 points, by considering these 3 cases, this covers every arrangement of 4 points. Every arrangement of 4 points on the plane cannot be shattered. As a result, 4 points cannot be shattered. For 3 points, there is one arrangement of 3 points that can be shattered. As a result, the VC dimension is at least 3. This is the tricky bit. Even one set of 3 points is enough to show that the VC dimension is 3. With 4 points, no set of 4 points can be shattered. And to show that no set of 4 points can be shattered, we have to even one labeling is enough. So with 4 points, to show that this arrangement is not shattered, we just need one labeling. To show that this arrangement is not shattered, we just need one labeling. So the quantifiers line up in an interesting way. If all 4 points are positive, that's not the case we care about. Remember, the definition of shattering has to try out every possible labeling. So for these 4 points to be shatterable, we need to show that every possible labeling can be matched by the classifier. And even if there is one counterexample, it fails. So this is, even though this might seem very simple, it gets complicated because of the way in which for every and for the such things interact with each other, the quantifiers interact with each other. Would 3 collinear points in 2 dimensions mean there's a redundant dimension? Would that put it in the category of the AB interval? There is an extra dimension, yes, but remember, our linear classifiers can actually go through that. The classifiers can, essentially there is a redundant dimension, basically. Yes. So in the 5 minutes that are left, I'm going to convince you that VC dimensions are interesting beyond the intuitive argument. It turns out that the VC dimension behaves like this quantity log of the size of the hypothesis space. And in fact, you will even prove it in your homework. So in the sample complexity results that we saw before, the sample complexity behaved depended on the log of the size of the hypothesis space. For consistent learners, and I'm going to state this without proving. Oh, there's a mistake here. There's H in H. The VC dimension of this thing gives us an Occam's razor result. If you have M examples, where M is more than this quantity here, and now everything gets more complicated, but what I want you to really focus on is just this thing here. If M is greater than that quantity there, then with probability at least 1 minus delta, the hypothesis has an error less than epsilon. If M is polynomial in the dimensionality and all that stuff, then we have a and we have a pack concept. To be efficient, we need to, of course, show that this can be learned efficiently. In the case of agnostic learning, where we don't know whether the true concept lies in this class or not, whether, for example, we don't know whether the true concept is linearly separable or not, we just want to use linear classifiers, then we get this we get a bound that's rather hideous. But once again, the key thing here is that there is this dependence on the VC dimension. What this says is that the true error, the generalization error, is no more than this quantity plus the training error. So the fact, ignore the details of what's inside that quantity. The important thing is it depends on the VC dimension. So in both cases, what we have is this result that says if the VC dimension gets really large, then learning is the generalization error can get really large, because the bound the bound gets weaker. We can't really guarantee anything more. Here, if the VC dimension gets really large, we need a lot more examples to guarantee that learning is going to succeed. And so in both cases, VC dimension behaves very much like the log of the size of the hypothesis class. Let me wrap up. As an exercise, if you want to play with VC dimensions, think about the class of axis parallel rectangles. We saw that at the beginning. And think about what should be the VC dimension. It's a fun class of functions to think about, because it will force you to kind of revisit the whole thing again. And your homework also, you'll be measuring the VC dimension of functions. This wraps up our whole thing about pack learning and learning theory. You need to know what is pack learning. And the focus is on generalization error, not training error. We considered two classes, two situations when we have finite hypothesis classes and infinite hypothesis classes. In the finite case, there was this connection between the size of the sample, the hypothesis space, and the sample complexity. You need to be able to derive and understand the sample complexity bounds that we saw. Basically, you need to know how to count the size of these functions. In the case of infinite hypothesis classes, which we saw today, you need to know what is shattering and what's VC dimension, and how to find the VC dimension of simple concept classes. Basically, the key point is VC dimension is a higher VC dimension gives more, leads to a larger sample complexity. The question on the chat is, what do I mean by the VC dimension behaves like the size of the hypothesis class? It's exactly right. Basically, the VC dimension of a finite hypothesis class is at most the log of the size of the hypothesis class. And in fact, you'll be proving this in one of the questions in your homework. Now, there's always this question about why do we need this stuff? There's the computational learning theory, remember, started with the definition of pack learning, which assumes the fixed but unknown distribution assumption. We saw Occam's razor and all that, and there's a lot of extensions to this theory. One extension that is actually interesting and an important one is this notion of this idea of pack-based theory, which makes some assumptions about if the prior distribution of the hypothesis spaces and shows that we can do we can show more interesting results. But why do we need this stuff? It answers questions like, what is learnability? It answers this question that how good is this class of functions that I'm thinking about? Is this concept learnable? How many examples do I need? One interesting thing that connects the two answers to this question that we've seen, Mistake bounds, it turns out, implies pack learnable. If a concept class is mistake bound learnable, then I've not proved it, but it implies that the concept is also pack learnable. But more importantly, it raises theoretical questions. And I'm a minute over time, and let me just wrap up with just this one thing. It raises interesting theoretical questions. I'll talk about the second thing. We've seen this bound, right? This true error is training error plus VC dimension and all that. Can I use this to define a learning algorithm? It turns out this particular bound that we saw directly leads us to one of the most important things that we build a lot of modern machine learning, which is the notion of risk minimization or loss minimization. And in particular, it directly gives us this class of algorithms called support vector machines, which is what we'll encounter next. All right, I'll stop here. We are now going to go back into defining learning algorithms and such things, and there'll be less theoretical stuff. So I'll stop now, and we'll pick up on Tuesday. Don't forget to start your homework, and in some sense, the homework will kind of give you things to make you revisit all these lectures. All right, I don't have time for questions, so we'll pick up on Tuesday.